Welcome to AP Podcast 8.3. This is going to be on dipole moment. And we talked a little bit about this last time with the polar molecules. And so I just want to go over this because sometimes students see this phrase and it kind of bothers them. Dipole moment, what does it mean? Well, really, all it means is that a molecule is a polar molecule. So, again, our simple example is HF. You've got one side that's a little more electronegative and one side that's a little more electropositive, but it is a polar molecule. It has a dipole moment. I'm not 100% sure if the moment has to do with the fact that, well, electrons are moving around and overall the fluorine side is going to be more negative. There are probably others out there that know that, but what we're going to do is just kind of dig a little deeper into these polar molecules. Now, which molecules are polar? Well, any two atom molecule is going to have a polar bond, with the exception of something that's bonded to itself. So if you're talking about some kind of O2, right, or an N2, those are not going to be polar. But any two atom molecule is going to be polar. Now, if we're talking about three or more atoms, there's a couple things to consider, and for the most part, we've really got to be able to look at the structure to decide whether or not a molecule is going to be polar or not. And the best way to show you this part where it says the geometry or symmetry can't cancel out the polarity is just to show you with some pictures. So let's look at a couple pictures. So here we have something that the polarity, we can think of it as going this way, okay? More electronegative going that way, or more electropositive, it really doesn't matter. And you can imagine this being something like, I don't know, carbon dioxide, okay? So when you have a molecule like this, the fact that this is more negative over here and more negative over here leads this molecule, because these directions of the polarity are equal and opposite, allows this to be a nonpolar molecule. So a linear molecule will be nonpolar. However, what would be a different situation? What if I put like a nitrogen here? Okay. So if I had different elements on this side, their electronegativities would not cancel them out, and therefore you would have a polar molecule. So it really depends upon what atoms are there, and do the dipole moments cancel each other out. Let's look at another atom or another molecule. This one has three things. You could think of this. There's a couple molecules that I could think of that look like this, like for example, boron tetrafluoride, BF3. Okay, or you could have something like ammonia. And again, if we're talking about the same element on each side, if these were all fluorines, then you could see that the dipole, the way the polarities are go, they cancel each other out. They're equal and opposite, and that would be a nonpolar molecule. What would be unique, though, is if I had something like, instead of fluorine had a carbon there. Something like that, okay? But again, a little different situation, but we want to just focus on this planar triangle. Here is a tetrahedron, and those of you that were with me last year know all about these shapes. You could think of something like a CH4 molecule, like a methane molecule, okay? All the dipole moments, they are all canceling each other out. So this is a nonpolar thing, all right? Again, it could be different if we put any other element other than hydrogen on the outside there. Okay, here's some that don't cancel each other out. Sometimes you get a bent molecule, and the most common one is water. So O and H, okay? And so we've got this side that's a little more negative and this side that's a little more positive, okay? And so there's, in a bent molecule, the directions here, they do not cancel each other out, and so you get a polar molecule. Here's another example. Oh, by the way, before I move on, I should mention that the fact that there's going to be some lone pairs of electrons sitting on this atom, that's the main reason for the polarity, or at least the negativity. Now look at something like this. Here's another one, a trigonal pyramidal shape. Imagine ammonia, because that's probably the easiest example here. I've got nitrogen with its lone pair of electrons. I've got some hydrogens here. And you can see how these guys are all pulling in equal and opposites, but I've got this area here where there's more negative, and so this is a polar molecule. All right, so those are the main shapes with molecules and whether or not their polarity will cancel each other out. And when we get into Vesper theory, we'll look at it a little deeper.